I'm going to show how to fit a straight line to a set of data points that I've previously entered. This procedure is called linear regression, and I'm going to use the well-known linear regression formulae, which can be found in a variety of places. I'm going to look at my favorite web browser and type linear regression into my search engine, and a few links come up. It so happens that the simple linear regression formulae has its own Wikipedia page, and I can scroll down and I can find the formulae for fitting a straight line here. And if I wish to fit a straight line y equals alpha plus beta x, beta is the gradient, alpha is the intercept, the formula which give the best estimates of the gradient beta and the intercept alpha are given here. And they're given in a variety of forms, and I can enter these formulae. I have a free choice about what I want to do, so I'm just going to choose one of them. I'm going to shrink that window down a little bit over there, and on the left hand side I'm going to create a new script to do my fit. Now, to begin with, I'm going to create some fake data, but of course you can appreciate that this can be changed later to work on any real data I have. So I'm going to create values of x that run from 1 to 20, and because I want to test my code, I'm going to start by defining a set of y values which are equal to 2 times the x values, and there's a very simple formula for doing that, of course. Now if I look at, I'm going to choose the third line in this formula, x y bar minus x bar y bar over x squared bar minus x bar squared. And so I need to calculate the means of various variables. So how do I calculate a mean? Well, programming languages may have the word mean defined, or they may have the word average defined. In MATLAB it happens to be mean, which is quite handy. So I can go straight ahead and I can define each of the variables in this formula, which I'm going to do so that I can keep clear what it is I'm calculating. So x bar, well, that's simply equal to the mean of x. Y bar is equal to the mean of y, and notice that MATLAB automatically knows how many elements are in x and y when calculating the mean. So that was straightforward. X bar squared is equal to x bar to the power of 2. It's a single value, but just for safety I'm going to put a dot in there. And I need to calculate x squared bar as well. So how will I do that? That's the mean of x dot power 2. So I'm squaring each and every element in x and then taking the mean of that. Oh, I should have given it a value, shouldn't I? Which is x squared bar. So I'll need to be a little careful about keeping clear what the difference between those values are. And finally, I need to calculate x y bar. So that's the mean of x times y. So x dot star y. And I want to calculate, so that's x y bar is equal to the mean of that. Now, obviously there are linear regression formulae built into MATLAB, but I'm just showing how we can do this using directly the formulae. So let's calculate what the estimated value of the gradient is. I'm going to use mest for m the gradient instead of beta, and I simply have to type in the formula now, which is xy bar take away x bar times y bar, and just put a bracket around it to make sure that I'm calculating everything in the right order, and I'll put a bracket at the bottom for the denominator, and I want x squared bar, see what I mean? You have to be a little careful, take away x bar squared, x bar squared. There we are, and that's our estimate of the gradient. And then to estimate the intercept, I'm going to call that cest, or estimate of c, I simply need to calculate y bar take away mest times x bar. And that's it. So let's save that. And I'm going to call that lin reg test or something like that. Okay, let's see if it actually works. Have I made any mistakes? So I'll run it, and aha, you can see here, if I expand out this window, that mest has been calculated to have a value of 2 and cest a value of 0, which is as it should be because of the way in which I've calculated y values to go with the x values. But let's test it a bit more. Let's change the gradient to be 3 and run it again. And you can see that it's changed to 3 on the right hand side. Let's add an intercept. Let's add plus 2 and we'll run it again. And now the estimate has become 2. Let's, just for good measure, take away 3 and the estimate is now 3. So for data where there is no random fluctuations, because of course this is all perfect data, I do indeed return the gradient and intercept that I expect. But let's see if that still works if I add some kind of random fluctuations. Well, let's I think we'll have to use a for loop to do this. We'll say for I is equal to 1 to the length of y, and put an end at the end there. And for each value of y, I'm going to add a random number. So to each value of the ith value of y, I'm going to add a random number, but because that random number is generated between 0 and 1, I'm going to subtract 0.5 so that the average value that's added on is 0. So I should return the same gradient approximately and the same estimate approximately, but I will get a fluctuation each time I run it. Let's try that again. Okay, so there you go. So the gradient is now no longer an integer, and neither is the intercept, but we are getting what we think actually are the correct values of the gradient and intercept. And I can generate more values of x. Let's create a longer line that goes from 1 to 200. And there we are, it still works. And in fact, of course, as I generate larger and larger numbers, larger and larger amounts of data, then the fluctuations away from the idealized value, if there were no error, gradually reduce. Now I'll leave it as an exercise for the reader how to go on from this and now taking the estimated values that I've generated with these gradient and intercept estimates, I can now generate the fitted values of that data. So for each value of x, I can now generate the fitted values of the y values. And of course from there I can now do a chi-squared calculation. And I'll leave that as an exercise for the viewer.